Hello, so I got a few questions about dependent motion, and I realized that I didn't go through a detailed example in class where the geometry is a little more complicated than some of the pulley problems that we did. So what I'd like to do is go ahead and record a video showing one of these problems to give you an example to follow. So the problem that I'm going to do is 12-217. This is from the 13th edition of the Hibbler text, so you can follow along if you have that. This problem states the crate C is being lifted by moving the ruler at A downward with a constant speed of VA equals 2 meters per second along the guide. Determine the velocity and acceleration of the crate at the instant S equals 1 meter when the roller is at B. When the roller is at B, the crate rests on the ground. Neglect the size of the pulley in the calculation. Then it gives us a hint. Basically, it tells us that we're going to use geometry to relate those XC and XA. Now this problem kind of babies you a little bit, and it gives you your own datum. It already has a datum set up. But in reality, most of the time, you're going to want to set your own datum. Keep in mind your datum always has to be fixed. You want your datum to be in a fixed position. So we have a pulley right here at the top, and we can see that pulley is bolted to the ground. That pulley's not moving. So I'm going to set my datum right there. And then I'm going to have two references. They say XC and XA. I like to use S because we use S for position. So I'm going to go ahead and write over this. We're going to have our SC here. Notice it goes to the bottom of the crate. And that's going to help us in a minute with some geometry. And then we have an XA here, which I'm going to call SA. And that's just the position of the pulley A with respect to the datum. And I have my arrows drawn nice and big so I know which direction is positive. So once I have that set up, I'm going to write down my givens. Crate C is being lifted by a moving roller A down with a constant speed of VA. So the velocity of A is equal to 2 meters per second moving downwards. In that case, it's going to be positive because you notice the arrow that I just drew moving downwards matches up with the arrow of my SA pointing downwards. So it's going to be a positive velocity. Determine the velocity and acceleration of the crate at the instant S equals 1 meter. So we're supposed to find the velocity of the crate and the acceleration of the crate when S equals 1 meter. When the roller is at B, the crate rests on the ground. That's another one of our givens. And that one we're going to have to do some investigation to see what that means. So I'm going to write that in given. Crate is on the ground. When A is at B. So when this pulley is up at B, the crate is resting on the ground. That's going to help us relate S to the initial SC and the initial SA, which we're going to need. Okay, so all we do now is we come up with an equation that gives us the length of the rope. Now I'm going to point out the rope to make it a little more clear. The rope is right here. There's the rope. And just for convenience, I'm actually going to make that rope go all the way to the bottom so that it lines right up with my SA. Now remember, the actual length of the rope is not what we're going to be dealing with. We're going to be dealing with the derivative, which is going to be the change in length. And we know this is an inextensible rope. So where the rope extends to is really your choice. Okay, so I have my rope, and now I'm going to figure out what's the length of the rope. So I'm going to say the length is equal to, well, we've got a section of it here. From here to here, as I color in the darker red there, that's going to be SA. I'm sorry, SC. The distance from our datum to the bottom of the crate, that's SC. Then we have this other part over here that goes from the pulley to A, and I'm just going to, at this point, I'm just going to label it. I'm going to call it the length from the pulley to A, LPA. And then I'll put in my equation plus LPA. Okay, so we have the length of the rope. Now we just need to figure out what LPA is. And in order to do that, I'm going to go ahead and draw another triangle. So the first thing I want to put on that triangle is I want to put that length, that LPA on there. Which means we have point A over here, and we've got the pulley at the top. Pulley is at the top there. Now we have to use some of the dimensions that are given. if we look at this top side here, the dimension for that top side is given as 4 meters. And the distance from the pulley to A, well, that's labeled as our SA. So with that triangle that we see here, we can use the Pythagorean theorem, and we can say that 4 squared plus SA squared is equal to LPA squared. Solve for LPA. It equals the square root of 16 plus SA squared. Okay, now we have our equation for the length of the rope is SC plus LPA, which we know is the square root of 16 plus SA squared. Now that we have the equation for the length of the rope, we're going to go ahead and take the derivative of it. So taking the derivative of it, we get the derivative of the length of the rope with respect to time. We're taking the derivative with respect to time is going to be equal to, the first one is just the derivative of the position of the crate with respect to time, plus the derivative of square root of 16 plus SA squared with respect to time. Okay, the first term here, the derivative of the length of the rope with respect to time, well, that would be the rate of change of the rope with respect to time. And we know this is an inextensible rope, so that is 0. The second one, dsc dt, that's the rate of change of the position of the crate with respect to time, which we know is just going to be the velocity of the crate. And then the last term there, we're going to have to use the chain rule to find the derivative of. So let's go ahead and use the chain rule. If you remember, the chain rule says that if we have a function, y, in this case, I'm just going to make our y a function of SA instead of a function of x, because SA is the equation that we have here. And I'm going to call that function square root of 16 plus SA squared. So if that is our function, then we can find the derivative of our function with respect to time is going to be equal to, well, I'm going to put my dy up here, my dt over here, and then I can fill in the dsa, because that is the variable that's given in our equation. So we know our chain rule is going to be the derivative of y with respect to SA times the derivative of SA with respect to t. So let's find this first part. Derivative of y with respect to SA. Derivative of y with respect to SA, that's just going to be one half 16 plus SA squared quantity to the negative 1/2. And then, of course, we have to take the derivative to the inside part. This is using the chain rule once again. And we get 2SA. Okay, that's part of our total derivative. But then we have to multiply it by the second term, dsa dt, in order to get dy dt. So our equation becomes, I'm just going to move the second equation down here, 0 equals the velocity of the crate plus, plug both of these in, and let's combine some terms. So we see there's a 2 and a 1/2, so those are going to combine. And then we have an SA on top. On bottom, we have the square root of 16 plus SA squared. And then, of course, we have the dsa dt, which is the other term we have to put in there. And dsa dt is just velocity of A. So there we go. We have 0 is equal to the velocity of C plus the position of A times the velocity of A over the square root of 16 plus SA squared. Part of what we want to find is the velocity of C when S equals 1. So I'm going to go ahead and solve for the velocity of C. It's equal to negative SA VA over the square root of 16 plus SA squared. So you notice to get that, we need the velocity of A, which is given, but we also need the position of A. Position of A is what we have to find out next. So the position of A, they give us that we're supposed to find it when S equals 1. Well, S is this little distance down here. S is equal to 1. So if we look at the entire thing, I'm going to redraw this, but I'm going to redraw it when pulley A is up at point B. If I redraw it when pulley A is up at point B, we're going to have the crate sitting on the ground. And then we're going to have a rope that goes up over the pulley and comes straight over. because we know that the crate is on the ground when A is at point B. That was one of our givens. So if we now trace the total length of the rope, this red part, the total length of the rope is going to be our 4 meters here and 4 meters here. So we have this one is 4 meters and this one is 4 meters. It said to ignore the size of the pulley in our calculations. So we know the total length of the rope is 4 meters. So if S equals 1, when S equals 1, we take that initial 4 meters and we subtract 1, and we can say that when S equals 1, SC is going to be equal to 4 minus 1, which is equal to 3 meters. So we have SC. Then we have to look at SA. Well, we already have an equation for the length of the rope with respect to SA. We know that the 4 doesn't change, and we know that the length of the rope is 8 meters. So if SC, the total length of the rope, we are using this equation again, the total length of the rope is equal to SC plus LPA. We know that the total length is 8 meters, because that shows on the picture above us here. And that's going to be equal to SC, which when S is equal to 1, SC is 3 meters, plus LPA, which is the hypotenuse of our triangle there. So LPA equals 5 at this particular instant, 5 meters. If LPA equals 5, we can go back and look at our triangle that I'm putting a box around right there. Our triangle in the middle here, if LPA is equal to 5, notice that we have a 3, 4, 5 triangle. We have 4 on top, 5 is the hypotenuse. That means that SA has to be equal to 3. So SA equals 3 meters. We have SC equals 3, SA equals 3. Now to find the velocity of the crate when S equals 1, we just plug in our values. The velocity of the crate is going to be negative SA, which is 3 meters. Velocity of A is given as 2 meters per second. Those are multiplied together. I'm just going to erase my SA and move it up so you don't get confused with the equation. Over the square root of 16 plus SA squared, and SA is 3 meters squared. Hopefully you can see that our units cancel out. On the bottom we have the square root of meters squared, which is just going to be meters. Then on the top we have meters times meters per second. So those 2 meters cancel and we end up with just meters per second. So our units are working. When you plug that into your calculator, you end up getting negative 1.2 meters per second. Okay, so the negative 1.2 meters per second, we know that negative means it goes in the opposite direction of the arrow. Our SA arrow is pointing down. So when we report the final answer, I would write that the velocity of the crate is equal to 1.2 meters per second going up, which is the opposite direction of our VC arrow. Sorry, it got a little squished there. Okay, we answered the first part of the question. We found the velocity of the crate when S is equal to 1. Now we just need to find the acceleration. I'm going to start a new page here, and I'm going to write our velocity of the crate equation. Velocity of the crate is equal to negative SA VA over square root of 16 plus SA squared. Okay, we also know a few of our givens, or a few things we found out, is that when S equals 1 meter, SC equals SA equals 3 meters. That's what we just found out a minute ago. Okay, with this information we can now march forward and we can find the acceleration of the crate at this instant. In order to do this, we're going to have to do the product rule. And I'm just going to go ahead and rewrite this equation as the velocity of C is equal to negative SA VA, and then I'm going to bring this up and call it 16 plus SA squared to the negative 1/2. And you can see that we have three functions multiplied together. And I'm going to go ahead and write the product rule, because that's what we're going to need to use here. The product rule, and now I have another video that you can watch that goes through how to use the product rule with three functions. The result of that video is that the product rule, if we're taking the derivative of three functions, a, b, and c, multiplied together with respect to time, that's going to be equal to the first two times the derivative of the third plus a times c times the derivative of the second plus b times c times the derivative, times the derivative of the first. That's right. There we go. So what I'm going to do now is I'm going to assign a, b, and c to what we have in our equation. This is going to make it a lot easier basically for bookkeeping, for organization, because this can get a little bit messy. So the first thing I'm going to do is I'm going to say, well, the a is equal to negative SA. I'm going to leave that negative in there just so I don't forget it. So a is equal to negative SA, b is going to be equal to VA, and c is going to be equal to 16 plus SA squared to the negative 1/2. Now what I can do is I can go through and I can find the derivative of each one of those, because we see that that's going to be in our equation as well. So dA dt, this one's pretty easy. The derivative of the position is going to be d negative dSA dt, which we know is also VA. The derivative of position is velocity. Now we're going to take the derivative of b. The derivative of b with respect to time. Well, the derivative of velocity we know is acceleration. I'm going to write it longhand here. Derivative of velocity with respect to time is equal to the acceleration of a. And then c. Just like we did previously, we're going to have to take c and use the chain rule. So the derivative of c, I'm going to use a new line down here. Derivative of c with respect to time, that's going to be equal to the derivative of c with respect to SA times the derivative of SA with respect to time. Okay, let's do the derivative of c with respect to SA first. That's just going to be negative 1/2. Bring the negative 1/2 down. Multiply it by 16 plus SA squared to the negative 3/2. Now we have to take the derivative of the inside part, which is 2SA. Okay, with that, we got the first part out of the way. But we can't forget that second part, dSA dt. Got to make sure that's in there too. dSA dt. There we go. So now we have the derivative of c with respect to time. Now it's just a matter of plugging everything in. I'm going to go back and I'm going to use this equation and simply write out the entire derivative using that equation. The very first one is a. Okay, so the derivative of a times b times c, well, on the left-hand side, that's just the derivative of the velocity of c. The derivative of the velocity of c is the acceleration of c. So I know that's the left-hand side, the derivative of this left-hand side. That's going to be equal to ab times the derivative of c. A is negative SA, B is VA, and then the derivative of c, I'm going to go ahead and clean it up a little. The derivative of c, I notice there's a 2 there, there's a negative 1/2 there, so the 2 and the 1/2 can cancel each other out, but we still have that negative. We know that dSA is a VA, so we're going to say negative SA VA, and then I'm going to go ahead and put the 16 plus SA squared cubed square root, and we have something that looks a little bit cleaner. Now I can go ahead and plug that down here, and it's multiplied by negative SA VA over the square root of 16 plus SA squared cubed. Okay, that's the first term. I've now handled the first term, and now I'm going to add the second term, which is A. A is negative SA. I'm just going to use parentheses so we know where that negative sits. Negative SA, C is 16 plus SA squared. I'm actually going to clean that one up too. That's just 1 over the square root of 16 plus SA squared. I'm going to go ahead and put it on the bottom. Square root of 16 plus SA squared. That's my C. And then I have to take the derivative of B. The derivative of B is just the acceleration of A. We've already found that. Acceleration of A. Okay, we just got the second term taken care of. Now I'm going to take care of the third term. The third term is B. Now B we know is just VA. C, now C is 1 over the square root of 16 plus SA squared times the derivative of A. The derivative of A is already up there. It's going to be negative VA. There we go. We have all of our terms. Now I can clean it up a little. The acceleration of the crate is going to be equal to, we have two negatives here, so they're going to cancel out. So we have an SA squared, a VA squared on the first term, over the square root of 16 plus SA squared quantity cubed. That's to the negative 3/2. Go to the second one, we have a negative sign that doesn't get canceled out, and that's just going to be SA AA over the square root of 16 plus SA squared. Okay, the third one we also have a negative sign, and that's just going to be VA squared over the square root of 16 plus SA squared. Okay, well we have our answer here. Now we're just going to have to plug in some numbers. And as you can see, is it a complicated derivative? Yes, there are some complications to it. You have to use the product rule and you have to use the chain rule. But hopefully you can see if you do careful bookkeeping and you make sure to have all the pieces, you can really put the equations together fairly quickly. I really do recommend assigning some substitution, like your A, B, and C like I did, and just do careful bookkeeping. Let's go ahead and plug in our values now. Now we know that SA is going to be 3 meters. We know that VA is going to be 2 meters. That was another one of our givens that I should write here. VA is equal to 2 meters per second. If we look down in our equation, the only other unknown that we need is the acceleration of A. Now the acceleration of A wasn't specifically spelled out, but let's go back and look at the problem. The crate C is being lifted by moving the roller A downward with a constant speed of VA equals 2 meters per second. So if it's a constant speed, that means it's not accelerating. So the pulley does not have an acceleration, meaning the acceleration of A is equal to 0. I'm going to go ahead and put that up here. And now we can plug in all of our values. AC is going to be equal to SA, which is 3 meters, squared VA, which is 2 meters per second, squared over the square root of 16 plus SA, which is 3 meters squared quantity cubed, minus SA, which is 3 meters times 0 meters per second. Oops, I did the wrong units. Meters per second squared. 0 meters per second squared over the square root of 16 plus 3 meters squared plus, sorry, it's a minus, minus 2 meters per second squared over the square root of 16 plus SA squared, which is 3 meters squared, equals. Okay, we have all our numbers plugged in, and now all you have to do is plug that into your calculator. Plug it into your calculator, and we get negative 0.512. And when we check the units, we can see that we have meters per second squared times meters squared divided by meters cubed. So the meters cubed is going to cancel out 3 of the meters squared, the meters to the 4th on top. So we end up with meters per second squared, which is exactly what we're looking for. Now we notice it's a negative number, and we're looking at the acceleration of c, so we have to go back to our original picture, and we say that our arrow for SC, which is right up here, the arrow for SC is pointing downwards, so if we have a negative, our final answer for acceleration is going to be the acceleration of the crate. I'm sorry, let's use consistent notation. Acceleration of the crate when s equals 1 is going to be equal to 0.512 meters per second squared upwards, the opposite direction of our arrow in the original drawing. So we have both of our answers for this problem. Great, I hope that was helpful to you. Please let me know if you have any questions. When you're doing these types of problems, it's very important to go through it carefully and slowly, and then you only have to go through it once, as opposed to going through it quickly and making mistakes. Make sure that you remember that dSADT that is needed for the chain rule. It's very important. Thanks a lot.